Good afternoon. This is David Eastwood, Geotech Engineering and Testing. Welcome to Case Histories and Mobile Crane Concrete Pump Truck Failures, Crane and Concrete Pump Truck Failures. So we getting involved in these crane failures. There's three case histories here, but we just got another one that some of these cranes are failing. So it's kind of interesting why some of these are failing. So let's see if you can get this thing moving. Audience, we have about 200 people RSVP'd. A lot of engineers and contractors have RSVP'd. If you need to reach me, my name is David Eastwood. My email is de@geotecheng.com. My phone number is 713-699-4000. This is going to be on YouTube. There's a lot of information here, so you may not get it all in one shot. So we have a whole YouTube channel. You can go out there and watch a webinar and send us an email, and then we send you a CEUs or PDH. So there's a 25, 30 presentations in there. You can go watch them, and we'll send you a PDH for them. This is going to be on there. If you have any questions, of course, you go to click on Q&A, and I'll answer the questions as I go through. Hopefully, we can do that. Zoom has changed the program so much that it's hard to make it to work very well. So we'll see it works this time. Geotech Engineering and Testing, we've been around for 38 years. We're located in Houston. We do geotechnical, environmental materials, and geoforensic engineering. We got a staff of about 60 people. Engineers, technicians, geologists. We work all over Texas, Louisiana, New Mexico, and Oklahoma. And we have our own rigs, so we're full service. We got our rigs, laboratory, geotechnical, material testing, and forensics. So we're going to be talking about cranes. These cranes are basically mobile cranes that we're talking about. They got outriggers, you can see that, and they got pads underneath them. These pads are very important when you have cranes. They have to be properly designed, otherwise you're going to get punched through, or you're going to get they break up, or if the soils underneath are not any good, they fail. And these are some of the cranes that have failed. This one probably has got a bearing capacity problem. You can see a big picture here. And so here's another one. Here's another one. It's got a bearing capacity failure. To calculate bearing capacity for these cranes that haul this stuff out there, if this is the initial crane, the load is uniformly distributed. As you pick up the load, depending which direction you go, you're going to have more stresses at the toe. Here you got, because of the lifting condition, a lot of the stress over here. So you really need to worry about the bearing capacity in here. We're doing a lot of bearing capacity analysis for cranes for a lot of these industrial projects throughout Texas. So this is how you calculate the bearing capacity failure. You use Bush-Ness or Westergaard stress distribution, knowing source shear strengths, and you can calculate bearing capacity for these cranes. If you're near an edge, you got to be a certain distance away from the edge. Otherwise, you're going to have bearing capacity failure. Because you're close to the edge, if there's a sloping edge, this is kind of like a failure surface. You can see it, that you have to calculate to see if you have adequate skin friction against sliding, or you're going to have settlement problems. If there's soft soils, you're going to experience differential settlement. And you can see the loading in here. Again, you're going to have certain distance from the edge. So you're going to analyze it if the crane is going to work short term or long term. Doing the construction is short term, but if the crane sits there for a long time, The soil parameters become long-term, they behave more like sand. So you're gonna have to run the check for short-term and long-term. And use the lower factor of safety for your design. Case history number one, this is Texas Medical Center. That was a few years ago. They had these concrete trucks that they were delivering concrete using these buckets. This is a 2-yard bucket. If you get 2-yard bucket, it's about 8,100 pounds of load of concrete. That's a lot of load. So they were delivering to the side of the construction, and you can see the crane over here, and it, basically moving down the bucket. And there are people working out here, and all of a sudden, as the bucket is coming down, the crane flips over, and the outrigger sinks into the sandy soils out here, which was not properly compacted. So you look at some of the pictures of the crane failing and the bucket. The guy was in here. This bucket fell on his leg and really, had a major problem. I don't know if he had to amputate his leg or not, but there was definitely a lot of damage to the guy when the bucket fell on him. And so that's 8,100 pounds. These are some pictures of the you see the crane in here. These are the outriggers. They didn't put a whole bunch of padding underneath them. And you can see this is how the outrigger sank into the soil. It's just got buried in there, loose sand. That was the outrigger. The padding was only 2 foot wide, and so it was not really working real well. The bearing capacity of these soil is low. These loose sand is about 1,000 psf. The outrigger was about 2.25 square feet. The pad was 2.25, so it was really the same size of the outrigger. So when we tested it, ran some standard penetration tests with rig, got soil sampling, look at the samples, ran density tests and all that. Allowable bearing pressure for the sands was 1,000 psf. The actual loading was like 5,000 psf. So we had actually a bearing capacity failure. You had to basically punch through the sand, and the rig kind of tilted. There was major litigation. Everybody got sued, and a lot of people had to pay money. But that's kind of a deal on this case. When you use a rig, you got to always check the soil on these cranes and make sure you don't have a bearing capacity failure. And all the padding got to be designed based on actual loading. And also you got to check the compaction. If it's a proctor for your job, we had a moisture content of 7 and density of 105. So if you check that, the percent of compaction was only 88%, and you need at least 95% compaction. So causes of failure was bearing capacity and settlement. Here's the case number 2. That's near Tyler, Texas. Introduction, project timeline, field exploration, lab testing, engineering analysis, summary, and conclusions. Let's see. Yeah, nobody's got any questions, I guess. This is a crane here. It's a concrete pump truck failure, and you can see this is flipping over. Look at the arm extending all the way down in here. This is on May 15, 2019, and the worker was killed. The guy killed. This thing hit the guy on the head and died when it flipped over. Here's the arm in here. Pumping concrete in here. You can see the crane. Kind of tilting over. Look at the padding in here. It was like railroad ties. The pads, these are railroad tie pads. And they didn't put enough of them. They were not nice together, and so it punched through the soil. May 15, 2019, outrigger failure. May 29, OSHA was out there. May 21st, sheriff's office was there. May 31st, inspection of the truck. January 31st, concrete pump truck outrigger inspection. October 2020, we went out there and did a site visit and field exploration. Site visit. We used GPR, ground penetrating radar. We did drilling and sampling. We did test pit excavations. Here's the area where the crane was, the pump truck was. These are boring locations: B1, B2, B1, B2, B3, B4. We did test pits: test pit 1, test pit 2, test pit 3, test pit 4. We did 4 test pits. GPR is basically a non-destructive testing that uses a electromagnetic energy similar to what cell phone use. A receiver is located within the antenna, receives the reflected signal when it encounters an interface of two materials with contrasting dielectric properties. So you send a signal, when you hit something, comes back up, you get it in here. This is the actual GPR machine that we use on the site. We mapped the whole area for high moisture, for voids, using GPR. That's where the crane, the concrete truck was. We also did borings out there to see what kind of soils we have. We had sandy clay soils out there. These are sandy clay soil samples. Lots of sand in it. The thing that was interesting here was the test pits. We used the backhoe, and we picked 4 locations out there near the outriggers, and just dug holes out there to see what we find. So we went out there and dug out to see what we find out there, checked the soil with the hand penetrometer to see what kind of a strength it had. And these soils had a hand penetrometer was 0.15. That's test pit number 1, which is only 300 PSF, very soft soil. Basically fill. This is test pit number 2. We started excavating test pit number 2, found a bunch of trash in it. And see all the plastic, all that stuff in it. A lot of trash in it. We found ties, railroad ties, old wood. Took a lot of trash out. This is test pit number 3. Lots of trash in test pit number 3. Chunk of wood. Hand penetrometer. We checked the soil with the hand penetrometer to see how strong it is. This one was 0.25. It's only 500 PSF. Pretty weak. We ran Atterberg limits, undrained strengths, Proctor test for compaction. Here are the soils. Fill. This is a lot of fill. 4 foot of fill of these borings. Here's 5 foot of fill in B5. Then below that was clay sand. And then we had lean clays and fat clays. This is boring number 1. You can see fill all the way to 4 feet. Lean clay with root organics. Below that, you had clay sand. We had sandy lean clay. So the PI of the soils was 19, 13, 17. Compaction near the surface passed, but at about 2-3 feet or so, it failed. Then it passed. So some of the fill was compacted good, some of it was not. This is test pit number, this is boring number 2, fill all the way to 4 feet, compaction passes all the way, PI of 1318, lean clay, strength of about 1,000 PSF, not bad. This is number 3. We hit something hard there. We thought it may have been a pipe, so we didn't go further. We checked the compaction, it passed. Had a PI of 24, lean clay soils. And here's boring B4. We had root fibers, a lot of trash in it. Soil strength was low. Density failed near the top. Pass, and at about 5 feet or so, it failed. So we had some of the densities fail here. We ran Proctor tests at each test pits. 112, 14. This is test pit number 1. That's a lean clay. Clayey sand, test pit number 2. You know, we got 107 and 17. Maximum dry density, moisture content 17. Test pit 3, we had lean clay again, 103 and 20, PI of 23. Test pit 4, we had lean clays, 114 and 13. Moisture content, PI of 16. So we got all this information. We did engineering analysis, and we look at the GPR results. We look at the aerial photos. We look at the rainfall data, soil profiles. We look at the bearing capacity of the soils. When we looked at GPR, it shows this is a possible utility from 2 to 3 feet, maybe a pipe or something here. Also possible voids 1 to 4 feet in these areas that are pink. These green areas, ground disturbance, there was some trash and stuff like that. High moisture content. So it picked up some stuff over there, disturbed soils in 2019. That's from aerial photo looking at it. We'll also look at the rainfall. You know, accident happened in or about May 15th. So before then, we had 4 inches of rain on May, May 3. And then we had about 2.17 inches of rain on May 8. And May 11, we had May 11, about 0.53 inches of rain. So the area was kind of got some moisture to it. Not very much, but it had some moisture to it. We had some rainfall before the actual putting a concrete pump truck on this site. So when we plotted the moisture of the soil against the dry condition and the wet conditions from PDR method, textile 124, when the soil is the driest, when the soil is wettest. Here is when the soil is the wettest, is the green. When the soil is the driest, is this blue. Our actual soil conditions are red. It shows the soils are pretty dry at boring B1. And look at boring B2 again, the soils are relatively dry. B3, they're average moisture conditions. They're not real dry, they're not real wet. So we checked the calculation, the bearing capacity of the soils here, and we came up with allowable bearing capacity of 2,100 PSF for the soils at this site, based on the shear strength of a 0.62 TSF, shape factor of 5.14, factor of safety of 3. So allowable bearing pressure was 2,100 PSF. Based on allowable bearing pressure of 21 PSF, that's 1 kilonewton per meter square is 20.1 PSF. So we got about 100 kilonewton meter squared. You need to have basically blocks of 6 inch by 6 inch and 5.5 feet long. That's the outrigger pad should have been look like, okay? This is not acceptable. That's how they should have looked like. So we look at the site. We saw, of course, GPR show the gas line in here, and look at also the historical data. This is what we looked at the some of the timber that we found out there underneath the outriggers that were just not connected together very well. They were pretty loose. That's what they look like. We found tons of trash out there where the crane was sitting. So, summary and conclusions. Based on the result of field exploration and laboratory testing, concrete pump truck outrigger failure occurred in the rear of the outrigger leg, in the back. Significant presence of plastic trash below the rear outrigger leg was out there, attributed to main reasons for outrigger support failure. In other words, they put the padding in there and it failed because the soil was very soft underneath it. And he had a lot of trash underneath it. So the area was supposed, I guess it was used as a kind of a disposal area for trash. They had a gasoline pipe going by the outrigger area. That again, the compaction of the soil above it was not good. Presence of voids, GPR showed some voids out there, high moisture areas. So all these things contributed to the causation for failure. Presence of trash, low string soils, poor compaction. So that's what caused the outrigger failure. This is a case history number 3. This is for a school. It's actual crane that kind of flipped over in Texas. That's near Dallas, the place. And project timeline, introduction, field exploration, laboratory testing, general soil conditions, engineering analysis, potential causes of failure. By the way, anybody's got any questions, please ask me a question as I'm going through these cases. Looking at this thing here, let me see. Okay, so far we have no Q&A, no questions, I guess. Here's the site near Dallas. This is kind of like the aerial photos. Just an elementary school going in there, brand new one. Lots of expansive soils. Site flat as a pancake. This is the school building. And this is where the crane was sitting, right here. So these are the padding right here. A lot of padding. The crane was lifting stuff and flipped over and just hits the roof. See how this is kind of flipping? It hits the roof, it damages the roof of the school. You can see that. Yeah, and all this litigation in it. And a lot of people got sued on this one. You can see the pictures of the crane. These are the outriggers in here. Outrigger sitting on top of the mat here. It punches the mat in here. Here. The outrigger, the outrigger, the outrigger, the outrigger. Soils are basically fat clays. That is steel plate on the below the actual the crane outrigger. We got a lot of pictures of this thing. Here's the crane hitting the wall. That was the CMU block wall. So damage. In March 3rd, 2023, the crane failure occurred. And about 2 p.m. in the afternoon, March 23rd, we were authorized to get involved in the project. And May 12th, 2023, we went out and did a site visit and borings and testing. We did site visit again, ground penetrating radar, drilling and sampling, test pit excavations. Here's the site. That's what it looks like. It's an elementary school, nice little school out there. You see the area here. It's a one-story school. We actually use GPR just like we did before. It's a useful tool for determining voids and high moisture areas. It uses an electromagnetic based instrument that can detect any kinds of embedded objects, underground utilities and high moisture. So here's what we're doing. We're using the GPR to locate voids and areas of high moisture. You'll see it running around everywhere. Just mapping the whole area. We also did a bunch of drilling and sampling. This is where the crane was. So we went out there, did a bunch of borings out here. These are the borings I'm trying to see what kind of soils we have. We are using our own rigs. That's the clays that are coming out, some fat clays. Really nice and hard. They're pretty hard soils. We also got a backhoe. Again, that's where the crane was. Got 4 test pits. Start digging the ground to see what we find there. Do we find any trash, soft soils, or what? We found a little bit of trash. There's a piece of wood there. So there's some more trash here. Going in there and checking that soil to see. Here's the fill. Here's the natural soil. The black stuff's natural soil. The gray stuff is the fill. You can see the natural soils, the fill. See, there's some plastic and stuff. Some wood. Steel. We checked with hand penetrometer to see how strong these soils are. So we found some trash in there, not very much, but some. Measure the depth. This is the natural soil. This is the fill. Hand penetrometer checking the strengths. Test pit number 1. We had 4 foot of fill material, fat clay. Below that, you had fat clay. Soil had hand penetrometer 4.5, which is pretty strong. There was no water. Test pit number 2 is the same thing. 4 foot of fill, hand penetrometer 4.5, no water. Test pit number 3. We had same thing, 4 foot of fill, and all the soil had hand penetrometer of 4.5. Test pit 4 the same way, real good, strong soil. So we ran classification tests, string tests, proctor tests. Here's the fill. This is the natural soil underneath. Everything was nice and hard. 0 to 4, we got fat clay. 4 to 25, fat clay. So we had a PIs of 35 to 46, 34 to 62, and shear strengths ranging from 0.47 to 2.5 TSF. It's relatively strong soils. It's test boring number 1. We had 4 foot of fill. Densities fail at 2 feet. Passed 0 to 2, 3 to 4 passed. You have PIs of 40 and 35. Shear strength of at least 1,000 PSF. Test pit 2, all the densities passed. And the PI was 46, shear strength of about 1500 PSF. Test bit number 3, we had densities, all pass, compaction of the fill, and the PI of 35 and 36. That's test bit number 4. All the densities passed, and the shear strength was about 2000 PSF. Pretty strong soil. These are the Proctor curves near test bit number 1, 97 and 23. PI 47. Test bit number 2, fat clay, maximum dry density 101, moisture content of 19.8, PI 35. Test bit number 3, we had fat clay, 99.4, maximum dry density, optimal moisture 22.5, PI of 41. And that's test bit number 4. Maximum dry density 98.7, optimal moisture 21.1. We reviewed the aerial photography and to look at see what was out there. Look at the topographic map, rainfall, and compaction data, and presence of perch water table. We'll also look at the soil moisture profile, potential vertical rise, PVR, GPR data, test pit data, bearing capacity. Aerial photos looking at the site back in the old days. Nothing was going on. This is 2005. There just was a basically just grassland here, some streets out there to build houses. 2011, just a pasture. 2015, just grassland. 2018, see the detention pond over here. That's the school right there. They got a bunch of houses that are going in. 2022, the houses are in. Look at the aerial photo. The area was very flat. There was really nothing topography to worry about. Rainfall. In March, we had about 1.2 inches of rain there. Not that much. Below that was bone dry before then. 0.1 inches of rain. So we got a little bit of rain there. Compaction, we ran the compaction tests. Basically, all the compactions passed in the fill soils. And boring, we won 1 to 2 feet compaction fail, but everything else passed. No perch water table in any of the test pits or the boring. There was no water. Moisture profile, we look at the moisture in the soil, the red stuff in the soil moisture in situ. Pretty dry. This is a wet soil condition. This is a dry soil conditions from PVR. 0.47 times liquid limit plus 2 is the wet. And the dry is, of course, 0.22 liquid limit plus 9. Ours was below that. That was pretty dry soil out there. Again, the red one is dry. Moisture contents are dry through underneath the crane. You can see dry boring B3, B4, dry, consistently dry soils out there. PVR, the PVR for this side was 2.7 inches. I guess go back to PVR. PVR is an index property of a soil based on textile 124 standard. It tells you how much heat you can expect as at a site. We have variable PVRs in Houston area, for example, can run anywhere from 0 to about 7-8 inches out there in Houston. So ground penetrating radar, we use the GPR to see if you get any voids and high moisture areas in the where the crane was, and you can see in here the red areas, potential void-like stuff. The pink areas, potential utilities 3 to 4 feet. The green area indicates ground disturbance, 3 to 6 feet. The black area indicates anomaly, 3 to 5 feet. The blue area indicates the high moisture. High moisture areas red void, like there's some voids out here. So it shows some anomalies out there with the GPR. Test pits, you know, they show some rock fragments and some plastic stuff out there. A little bit of trash. Not that bad. It was not very much. In general, the results of test pit, I've shown small chunks of wood, plastic, rock, no perch water table. So bearing capacity, the crane was in this area here. We checked the soil bearing capacity. We found shear strength bearing capacity of that soil is about 2,000 PSF. So that's, we calculate the load from the crane into the matting and bearing capacity. It was below 2,000 PSF based on factor of safety of 3. So the crane failed not as a result of the soil problem. Bearing capacity was not exceeded. We think that basically the crane failed as basically because of shifting of center of gravity. They picked up the load that got outside the center of gravity. Center of gravity is an important operating a crane. When you're operating a crane, when operating a cranes, a crane operator should always ensure that the center of gravity is maintained. So when you pick up something out there, if you're a crane, if you go out too far, this thing's going to flip. So we think that this thing flipped, not because of the soil, but because he had load on it, got outside the specific gravity. Because when you look at some of these failures here, you don't see that much soil disturbance. There's not that much soil disturbance near the outriggers. There's no pile of soil heaving up next to it. So we recommend that every time you got a crane job or a pump truck, go out there and do some borings out there and check the bearing capacity of the soils out there. And also you put that on your drawings if you're an engineer. Conduct soil bearing capacity check using geotechnical engineer for any crane or concrete pump truck outriggers that be used on a project site. So these are some good pictures. If you got projects that you have some pictures of them, send them to me. I appreciate that. We use them in presentations. You got my email. This presentation is going to be on YouTube. So you're going to go see that. Let me see, this thing works, the evaluation. I don't know if it works or not. No, it doesn't. So the pole doesn't work. So, hey, Vicky?
Yeah.
The pole does not work. So please send me an email. Tell me what you think of the presentation. If you need any improvement and stuff, send me, you got my email. My email is d@geotecheng.com. My phone number is 713-699-4000. We're going to have a bunch of webinars coming up. So we're going to send you notices of those webinars. You're going to get PDH hour after a week. So Vicky is going to send you that presentation and PDH hours. So it's very important, you know, to look at these things. Sometimes you may think that things are different perspectives. This is Mount Rushmore. This is the front of it. This is the back of it. Questions? I don't know if the Q&A has worked. Just type me a question, see if it shows up in the Q&A. Because we don't see, I don't see any questions. It doesn't show anything. Yeah, it shows 2 questions, but it doesn't show any of the Q&A. Let's see. Vicky,
Yeah.
can you come here, please? It doesn't show it. I mean, this is a new software, and we don't know how to make it work. We have Q&A 5 questions, but it doesn't show. Oh, see if the poll works too. Unless you got a magic finger. Okay, we just launched the poll. If you would answer the poll, see how I like this program.
I couldn't hear you on the computer. You're on my phone.
Question, nice presentation. So finding was operator error. It was, yeah, operator error really, in case number 3. But, I would say case number 1 and 2 was bearing capacity failure where,
Yeah, the pole came out.
yeah, so, that was bad stuff there. We got a question, is there an overarching recommendation you can make to follow apply this in the field? Again, anytime you got a crane project, you gotta check the bearing capacity, do a geotechnical work on it. So that's really important to do that. So these are all the questions that we got. I appreciate your time. Again, you're gonna get links on some of the other programs we're gonna have. Any other questions? Great. Well, you all have a great day. We'll be in touch. Thank you very much. Bye-bye.